Hello, everybody. So what we're going to be doing today is we're going to cover section 4.8 in your book, which is covering the topic of Lagrange multipliers. So Lagrange multipliers are a method of solving optimization problems, finding minimums and maximums, but it's kind of a different way than what we did in the previous sections. And also it only applies to a specific type of problem. It's a good topic. It is a topic that sometimes they kind of expect you to be familiar with when you get into other more advanced math classes. So it's good to, make an attempt at this. Also, I think these problems tend to be significantly less work than some of the problems in the previous section, and that's nice as well. In any case, let's go ahead and get started talking about it. So, what we're going to learn in this section is how to use the method of Lagrange multipliers to solve optimization problems with one constraint. So we're going to learn what a constraint is. The other thing we're going to do is we're going to use the method of Lagrange multipliers to solve optimization problems with two constraints. So really, that's just going to be the same thing. So there's not actually a lot to learn in this section. Uh, it's like a new technique. We'll see what it is and we'll try it out, and it will work pretty well. So just kind of a new thing. Not too bad. I think compared to the previous section, I think this should be less work. The last section was kind of a doozy. All right, so let's talk about what is a constrained optimization. I already have a lot of this written down because I already screwed up my video one time, and now we're redoing it. So let's hope for the best this time. So, what is constrained optimization? That's not something we've mentioned in this class before. So here's the idea, constrained optimization. So there is a function that you want to minimize or maximize. Of course there is, right? We're finding minimums and maximums. But the function that you want to minimize or maximize, you call it a specific name. We call that the objective function, right? When we're dealing with multiple equations, we need to be able to keep track of what is what. The one that you're trying to minimize or maximize, that's the objective function, okay? And usually for us in the problems, they're going to call that f of xy, or if there's three variables, it could be f of x, y, z. And it makes no difference to us whether it's 2 or 3. Obviously, 3 is slightly more work. Could be significantly more work, but the method's the same. Okay, so the one you want to minimize or maximize is called the objective function. However, this is constrained optimization. So there's a constraint. So what's a constraint? So the idea is that like the x comma y or the x comma y comma z, it's not just allowed to be any numbers. You can't use any x, any y, any z you want. There's going to be a separate equation. So not the objective function, another equation that x comma y or x comma y comma z also has to satisfy. And so that other equation that they have to satisfy is what we call the constraint. So it's an extra equation that we have to satisfy. So there's an objective function, and then there's a separate equation called a constraint. And we're going to write our constraints in a specific way. We're going to formulate them so that they're like g of xy equals 0 or g of xyz equals 0. You can always do that. Let me see here. So we don't need to write it, but you could say like x plus y equals 0. That's a constraint. Or, x squared plus y squared equals 4. You'd be saying that x and y have to be on a circle, right? But you wouldn't write it this way. You would want to write it in this form. So you would just move the 4 over to the other side and you would write it like this. Do you see? So whatever you have, you can always just move everything to one side of the equation and get a 0 over there on the right. And that's going to give you what we call the constraint. Okay, so we're going to just do one of these kind of naively without learning what Lagrange multipliers are first. and then we'll learn what Lagrange multipliers are. So here's an example of what one of these problems might look like. So find the minimum of f of xy equals 3x squared plus 4y squared. So that's a function. And then they say subject to, and then they have another equation. So you can see the difference here, right? Like this is a function with a name, and this is just an equation, bunch of stuff equals 0, and there's no name on that. Okay? So if you were looking at this and you were trying to figure out what the objective is and what the constraint is, well, the objective function is the one that you're trying to minimize or maximize. So it would be the f of xy equals 3x squared plus 4y squared. And then the constraint is just the extra equation that we have to satisfy. And there it is. Okay, so there's an objective function and there's a constraint, and that's what makes it constrained optimization. Now, if we were going to try to solve this, how would we go about it? And so there's a pretty, there's a straightforward way to try to do this that you could probably think of. So to find minimums and maximums, that involves like finding critical points and stuff, which means taking derivatives, setting them equal to 0, etc., right? So you have some idea how to minimize or maximize a function, but then you've got this constraint. So how do you satisfy this constraint at the same time that you're trying to minimize or maximize this? And the way that you might want to try it is as follows. What you could do is you could take your constraint here. So it says try to solve this with what we know, since we have to satisfy the constraint, which is 2x plus 4 minus y equals 0. What you could do is you could solve this for y. And if we do solve it for y, right, just move the y over, be very simple. You could make it say, I guess I'll also reverse the order, y equals 2x plus 4, right? So this is just the same, this is just the constraint again, just with the y moved over, and then also reverse the order to write it like this. So this has to be true in order to satisfy the constraint. So then what you can do is you can actually take this and you could substitute that into your objective function, and then that would make your constraint satisfied, because if you substitute this in, you're going to make sure that that's true. Okay, so we could do that. We could, so we know this, we could substitute this into the objective function. And, I'm not going to be too careful about how I do that. But so you have your f of xy, which is, let me just copy it, 3x squared plus 4y squared, 3x squared plus 4y squared. And if we just take the y and substitute that in, then like f of x comma, and then y is going to be 2x plus 4. So just substitute the 2x plus 4 in for the y, basically. We would get 3x squared plus 4, 2x plus 4 squared. And if you multiply that all out, you get 3x squared plus 4. You have to FOIL this. So we got 4x squared plus 16x plus 16. So you could multiply this all out, 3x squared plus 16x squared plus 64x plus 64. And then we could combine like terms. We would have 19x squared plus 64x plus 64. And you could give this a new name. You could call this just like, we could just call this f of x actually. And if you don't like calling it f, because the original one was called f, and now this just has a single variable, so it's not really the same f, then okay, fine, give it a hat. So f with a hat could be this. Okay, and this one right here has the constraint built in. So you would be able now just to solve this. Like this problem actually here, um, as it was given in the original problem, could have been solved in Calculus 1 with this technique, right? So this is something that you could do, because now if we had to find the minimum, so find minimum with Calculus 1 techniques, with so find the minimum with Calculus 1 techniques. So you would have to take the derivative. So you'd get 38x plus 64 for your derivative, pretty simple derivative. Set it equal to 0. 38x plus 64. Move the 64 over. Divide by 38. X is negative 64 over 38. I guess you can do negative 32 over 19. And you get that x value. Okay, and that's a critical point. You could double check using the second derivative test or the first derivative test. I'll do the first derivative test. Just briefly, because this is, again, not really what we want to be doing with our time. But let's say negative 32 over 19 here. This is where the derivative is 0. And then if you put a number that's on the right-hand side of this, like 0, into the derivative, which is up here, you would get 0 plus 64. And the point is that it's positive. So on this side, the derivative is positive. And if you put something on this side into the derivative, so this is less than negative 2. So like negative 5, for example, is definitely on the left-hand side. If you put that into the function, you'd have 38 times negative 5 plus 64, which is, I don't even know, but it's definitely negative, right? So I can tell that that's negative, and so it's negative over here. And then if you have a function that's decreasing because the derivative is negative, and then increasing because the derivative is positive, right? Negative derivative goes down, positive derivative goes up, then there must be a minimum right here, right? This is the bottom of a valley. So this is a minimum, right? So we know that from the first derivative test, we know, or we see, that x equals negative 32 over 19 is the location of a local minimum. Okay, so you get that. And then to get the corresponding y value, find the y value using, how would you find the y value? Well, you got the constraint equation somewhere, right? It's highlighted right here. Y has to be 2x plus 4. So the y is 2 times x plus 4. I need a calculator. Oh, I got one right here. Don't have to go too far. 2 times negative 32 over 19 plus 4. 12 over 19. Like that. Okay, and then so your solution is going to be this. X comma y equals, the x value was negative 32 over 19, and the y value is 12 over 19. And we did it. We solved it. Okay, and so that was a constrained optimization problem that we solved with a method completely unlike what we're actually trying to learn today. So 15 minutes wasted. But there was a reason I did it. I can't really share that with you right now. No, I can't. So here's the thing. So Here's some neat stuff about the problems that we just solved. Okay, so the objective function was this, right? The objective was f of x comma y equals, what was it? 3x squared plus 4y squared, I think. 3x squared plus 4y squared. Okay. Um, and the constraint, I need to write down the constraint, which we can write different ways. I think I'm just going to write it this way. Y equals 2x plus 4. Uh, that's not how it was given to us originally, but that's what it is. Now, here's the thing. If I go to some graphing software here, and I want to graph a couple of things. So let's open Safari, make this a little bigger, and we're going to do some graphing. So let's go to Desmos. We'll use Desmos instead of GeoGebra because we're only doing 2D plots right now. So if we look at level curves of this function, 3x squared plus 4y squared. So a level curve of that function looks like this, like 3x squared plus 4y squared. And then if you do equals something, then you get the curve. And so they're ellipses, right? So they're ellipses. And if you change that number 1 to like a variable, so like if I go like, call it like A or something, I can add a slider there. And these are your level curves. Okay. Let me see if I can make this a little bit bigger, thicker lines and that sort of thing. Okay. So these are level curves, right? So like when I have it on 6.7, that's what A is right now. The level curve is function equals 6.7. If I go up to 10, there's the level curve for A equals 10, F equals 10, right? So you can get level curves, whatever level curves you want. Okay. Now let me put in this function, y equals 2x plus 4. Y, that's not the y I want. Let me go how numbers. Okay, there we go. Y equals 2x plus 4. Okay. So there is a line. Now that line doesn't change, right? And so an interesting thing happens. If I take this level curve, I can make this small or big. I can make it bigger. Let me change the, let's go like 0 for a minimum, and then let's go like 15 for the maximum, and let's go 0.1 for the step size. That'll be good enough. So I have all these level curves here, right? But there's something that happened at a special one. And that is you get what we've got in this picture here, where the constraint, the green line is the constraint, and the function we're trying to maximize, which we're looking at level curves of it here, there's a special level curve where the green line and the level curve are tangent to each other, and that's what I'm showing right here. Now, if I go back here and I look at the point that we found here for the actual answer, right, which was right here, negative 32 over 19, 12 over 19, let's plot that. So it's negative 32 over 19, comma, where's the comma, 12 over 19. Look at that. Isn't that interesting? That right where they touch, that happened to be the answer? It is, right? That's interesting. I think that's interesting. Let's screenshot this. Let's put that in our notes. Actually, you know what? Let's not. Sorry. The reason I don't want to do this yet, delete it, is because I forgot to do something over here. Um, so what is the function, right? Like I found this right here, but I didn't actually figure out the function value that goes with it. So our function was um, we've got it in different places. 3x squared plus 4y squared, right? So if you have f of, and I put in the negative 32 over 19 and the 12 over 19 into 3x squared plus 4y, which is 12 over 19 squared. Let me just figure out what this number is first of all. 3 times negative 32 over 19, close parentheses, square. Something terrible happened. Plus 4 times 12 over 19 squared. Boom. Oh, 10 point. Okay, so it's 10.1052. It goes on forever, right? So now that we've done that, if you come back over here, you'll notice that I've only made this so it goes by 0.1s at a time for the A. And so the closest one is 10.1. And that's actually the one that, the 10.1 was the one that looked correct, right? So if you actually zoom in, it's actually should be, they're not actually touching, right? But if I put in this number, 10.1052, then that would move the red curve right over to the green curve. I just don't have enough resolution to do that, but you can pretend that they are. Okay, so let's screenshot that now. Like this. Cool. Done. Save to photos. Okay. Can't believe that worked. That was amazing. Make big. So what you can observe from that picture that we just did was that the level curve, observe, the level curve for f of x, y equals 10.1052, whatever that solution actually was. And the constraint are tangent to each other. Okay. And where they intersect is at the solution. And the point where they intersect is whatever it was, negative 38, no, negative 32 over 19, negative 32 over, writing hard, negative 32 over 19, comma 12 over 19 is the actual solution we were looking for. Is the solution we found to the problem. Great, so what? The point of this is that there's actually a method for looking where you're trying to look for the solution to an optimization problem. And instead of looking for critical points, what you do is you look for this. You look where the constraint and the level curves are tangent, and then you find that point where they intersect. You find that point where that happens, and then that's your answer. Okay, and that's going to be the method of Lagrange multipliers. So let me say that, and then we can write down the formulas here. So Um, there is a method for solving constrained optimization problems where you don't look for critical points and so on. Instead, you look for a place where the constraint is going to be tangent to the level curve. So you look for an xy value on the constraint that where the constraint is tangent to a level curve. Okay, and that method is what we call the method of Lagrange multipliers. Okay, so that's our introduction. Now we can actually start talking about Lagrange multipliers. Okay, so I'm just going to give you the method now because we know the idea. The idea is going to be somehow we're looking for where this happens. So we're skipping critical points and stuff like that. We just want to know, where does this happen? And so here's the method. So we have let f and g be functions of two variables with continuous partial derivatives. At every point in some open set containing the curve g of xy equals 0. So that's your constraint. So basically what we're saying is we need the derivatives to all exist and be continuous and smooth and everything like that on a curve and around the curve. And the curve is just the constraint anyway, so we're only looking at the constraint. If the constraint's fine everywhere we care about is fine. All right, so suppose f, when restricted to points on the curve, right? So if you're restricting yourself to points that are satisfying the constraint, which of course we want to, as a local extremum, I should say, minimum or maximum, at the point x0, y0, wait, hold on. Suppose f, when restricted to points on g of xy equals 0, has a local extremum at the point and the point, the gradient of g at x sub 0, y sub 0 is not equal to 0, then there is a number lambda. I don't really know why they use lambda, but they use lambda, and that's called a Lagrange multiplier. for which gradient of f is equal to lambda times the gradient of g. It said lambda times the gradient, but I didn't write the gradient. Okay, now this sounds complicated, but it's not that complicated. So like, let me just draw a little picture that we had before, right? So let's explain why this makes sense. So suppose you have level curves. So I'm going to draw several level curves, and they don't need to be the level curves from the previous problem. That's fine. Okay, so like, let's say these are level curves of, f of x, y. Okay, and then you've got your constraint, which is g of xy equals 0. So the constraint could be any kind of curve. I'm going to draw it like a straight line again, just because that's the easiest. Okay, so let's say that that is g of x, y equals 0, that curve. And what happened was there's a point right here that's going to be your x0, y0. And that's the point that we're looking for. And the reason you can use this is, if you remember what the gradient does, the gradient points 90 degrees away from the level curve, right? So just recall gradient g, I'll just say gradient f actually, but gradient f points 90 degrees away from the level curve, right? They're orthogonal. So what that means is that if you come over here, the gradient of the level of the function f points out like that, 90 degrees away. So like, this is 90 degrees to that purple curve. Okay, oops, that is not what I wanted. Okay, so that's like your gradient f points like that away from the level curve. But guess what? You also have a gradient of the blue curve, which also points 90 degrees away from the blue curve. So like, maybe that one's like that. So it's a different length, but maybe that's gradient g. And so they're both 90 degrees away. And what happens is, because the purple curve and the blue curve, I kind of didn't draw it perfectly tangent, but the purple curve and the blue curve are supposed to be tangent. That means that their gradients point 90 degrees away from themselves. But because the two curves are tangent, that means the two gradients point in the same direction. Or actually, it would be possible for like the gradient to point, I'm erasing everything. It would have been possible for the gradient to, to point the opposite direction as well. That would have worked fine in the definition as well. But the point is that the two gradients have to point either in the same direction or the opposite direction, just based on the fact that they're tangent. The fact that they're tangent means their gradients are going to have to point in the same direction. And if you look at what this is really saying, this is a vector. So we're saying a vector is equal to a constant times another vector. So all we're really saying is that the two gradients point in the same direction. That's all that equation said. So all grad f equals lambda grad g says is that at the point we care about, the gradients are parallel. They point in the same direction. So same direction or opposite. Okay. And so that's what's going on. And we already said that the lambda there is just a constant, and it's what we call the Lagrange multiplier. Okay, I'm not going to prove this because I think we talked like enough about why it's true, or at least we saw that it was true at a particular example. Um, and then we know that you can believe that if the level curve and the constraint are tangent to each other, then of course 90 degrees away from that is going to be equal because of the same slope. So 90 degrees away is the same slope, and so on. Okay, so enough of that. I'm not going to prove it. The proof is in the book if you want it. What we want is how do you actually do this thing, right? So here's the actual method. So problem solving with Lagrange multipliers. Okay, so step one, they say determine the objective function, right? You got to know what you're doing here. So determine the objective function and the constraint. Right, I guess I should say the objective function f of x, y, and the constraint g of x, y. It is g of x, y equals 0, but constraint function. Okay. All right. Step 2, what you're going to do is you set up a system of equations, and this is the actual method of Lagrange multipliers. So you set up a system of equations. So your system of equations is going to be the gradient of f x0, y0 is going to equal lambda gradient g x0, y0. And then you have another equation, and the other equation is g of x, y, x0, y0 has to be 0. Okay? I have some comments to make about that, but I will just continue on and then I'll come back to this. So what you're going to do is you set up that system of equations. After you have the system of equations, you're going to solve it, right? So solve the system to find your x0, y0. That's your solution. Okay, and then so you're going to have possibly multiple options for your answer from step 3, and then what you do is you just evaluate the objective function f at any solutions from step 3. And the largest is the maximum, and the smallest is the minimum. And the smallest is the minimum. Now, don't have flashbacks to the previous section here. You're not going to have a million of these. This isn't like the previous section where there's like so many points to do. It's going to be much more straightforward. Okay, so I guess one of my first comments here is that it looks like there's 2 equations. There's actually more than 2 equations. So what's going on here is that remember that the gradient is a vector. So that means there's actually, when you write gradient f, there's actually an x component and there's a y component. So this is actually 2 equations, and then this is a third equation. So there's actually, there are actually 3 equations here and 3 unknowns. So the equations are like this, right? Because you know that the gradient is just the partial derivatives, right? So like you have your first equation is like fx equals lambda gx, fy equals lambda gy, and then your third equation is that g, I'll just write g equals 0 because I wasn't writing the x 0, y 0. So you have your three equations there, and then also you have three unknowns. Your three unknowns are the x0, the y0, and the lambda. So you actually have three equations and three unknowns. But we'll just see that when we go to solve it to do one of these. So we could do the same problem that we did before, or we can do a new one. Let's just do the one we did before. Why not? Just so we can see it, and then we'll move on. And of course, we'll do more complicated ones. So example. So find the maximum. Or no, we were finding the minimum. Find the minimum of f of xy. What was it? It was 3x squared plus 4y squared. Subject to, and it was 2x plus 4 minus y equals 0. Is that right? Let's just double check that. 2x plus 4 minus y equals 0. Okay, yeah, sure, that's fine. Okay, so let's just go ahead and let's just try to apply the method of Lagrange multipliers. So step one is we need to make sure we know what the objective function is and what the constraint function is, right? What's the f, what's the g? Because a lot of times they don't even say what the f and the g are. So I did, but not always. So f of xy is 3x squared plus 4y squared. Okay. Now what's g of xy? Nothing was called g, right? So you got to make sure your constraint is written in the correct form, right? Everything on one side. And then whatever that is, that's your g. Okay, so that's it. What's step two? Step two is set up this system of equations. So we actually have to find some partial derivatives here. So we need the gradient of f and the gradient of g, right? So we need to set up our equations. First thing we need is the gradients. So we need the gradient of f. So the gradient of f, remember, it's the partial with respect to x, partial with respect to y in a vector. So the gradient is, so partial with respect to x is just 6x, right? Partial with respect to y is just 8y. Okay, so there's your gradient f. We also need the gradient g, which of course is going to be gx comma gy. So what's the partial with respect to x here? It's just 2, right? Because there's only one x right there. So 2. Wait. Yeah, that's right. Then we need the partial with respect to y. Partial with respect to y here is going to be -1, right? This is the only y. -1, like that. Okay. And then from there, your system of equations is going to be this. So the system is its gradient f equals lambda gradient g, and then also you have g equals 0, right? Those are the two things you have. So we write it out. The gradient f is 6x comma 8y equals lambda 2 comma -1. And the other part is g equals 0, right? That was just the constraint. So 2x plus 4 minus y equals 0. So that's your system of equations that you have to solve. And it's not as bad as you think, right? Because I can just rewrite it. Like we don't have to keep these as vectors. You can actually write them out as separate equations as, right, the 6x equals lambda times 2, right? Like 6x lambda 2. Those have to equal each other. 6x equals 2 lambda. And then the other one, right, the 8y has to equal lambda times negative 1. Hold on. I should have written this the other way around. I don't know why I did. Easier to read that way, right? And then the third one is 2x plus 4 minus y equals 0. And so there's three equations and three unknowns. So three equations, and the three unknowns are the x. I didn't call it x0, I just called it x. The y, which we also don't know, and then the lambda, which we also don't know. So we don't know the lambda, but we know everything. Uh, I don't know what I was saying. I was gonna say we don't know the lambda, but of course we don't know anything here. So we just need to solve this for any way we can for the three variables, which is actually the next step, right? Step 3 is going to be solve the system, right? Using any kind of algebra that you want, using algebra. So how could you solve this? There's a lot of ways you could solve this. So for example, you could solve this for x. You could solve this for y. You can substitute those into this equation down here, and you could find lambda. After you find lambda, you'll know x and y. That's one way. Another thing you could do is you could solve this for y, like substitute that in up here, and then you've got two equations with y and lambda, and so on. So there's a lot of different ways you could do this. Here's how I'll do it. So if I number these, like maybe give them numbers here, like 1, 2, 3. So the way I'll solve this is I'm going to solve 1 for x. And I'll get x equals 2 lambda over 6, which is lambda over 3, right? Then I could solve equation 2 for y, and I'll get y equals negative lambda over 8, right? So I'm just moving the 8 over to the other side, dividing by 8. And then I can take both of these and I can substitute them into 3. So you have like 2x plus 4 minus y equals 0. But the x we just found is lambda over 3. And then the y we found is lambda over 8, negative lambda over 8. Like that. So you can work this out. Solve for lambda, which is your Lagrange multiplier. So you have 2 lambda over 3 plus lambda over 8. I'm just taking negative, negative lambda over 8. That's a 4. I'm going to move that over to the other side as a negative 4. Just trying to do some stuff. Then you've got 2/3 lambda plus lambda over 8. If I do 2/3, so if I do like 2/3 plus 1/8 lambda equals 4. I'm doing 2/3 plus 1/8 on my calculator. It is 19 over 24. Lambda equals 4. So lambda is 4 times 24 over 19, which is 96 over 19. Okay, so you have the lambda. Now, once you have the lambda, you can take that lambda and go back up to equations 1 or 2 and find x. Or actually, if I give these numbers down here as well, so like we have 1, 2, 3, if I call this 4 and I call this 5, you can substitute the lambda into 4 and 5 and find the x and the y. So I guess what was 4? 4 is x equals lambda over 3, which is 96 over 19 over 3. So you go 96 over 19 over 3, you get 32 over 19. Looks familiar. And equation 5 was y equals negative lambda over 8, which is negative 96 over 19 over 8. So negative 96 over 19 over 8, which is negative 12 over 19. What happened here? Did I make a sign error? My results are negatives of what they should be, aren't they? Let me figure out what happened here. Yeah, okay, figured it out. Right? Negative, no negative. Negative, 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 positive. Okay, there you go. So you find the x and the y, and we got the lambda, which we don't even care about, and we got the x and the y. So so we found xy equals negative 32 over 19 and 12 over 19. Okay, and so that's either a maximum or a minimum, one of the two. And, you know, one of the two. But we did the method of Lagrange multipliers and we found that point. So notice that like that whole method was completely different than finding critical points and stuff, right? But also it worked and it got us the answer, the same answer that we got using Calculus 1 technique. So that's the method of Lagrange multipliers, and it's it's fine. Let's try a different one here. Is this going to be terrible? Okay, that's three variables. No, that's 2 variables. Okay. You know what? We're just going to do it. I was trying to avoid a problem that looked hard, but like we shouldn't do that, right? We should just do the problem, and if it's hard, it's hard. Okay, example. So this is a word problem that I don't care about. I'm just going to write the equation here. So we want to say we got this function f of xy equals 48x plus 96y minus x squared minus 2xy minus 9y squared. So quite a bit more complicated than the previous problem. And so this is going to be like a profit model. So this is profit. For X golf balls sold per month. And Y hours of advertising. Okay. Now your constraint is um, this. So the constraint is going to be how much money you have to spend, basically. So they just say the constraint is 20x plus 4y equals 216, and somehow that's based on how much money they have um, to sell golf balls, how much money it costs to make golf balls, and how much advertising it costs. So this is what the constraint is. Okay, so let's just go ahead and get started. And what we're trying to do is we're trying to find two things. Find the x and y values that maximize profit, and the maximum profit. So a couple of things we have to do. All right, and we're going to use Lagrange multipliers. So use Lagrange multipliers. So because this one's more complicated, I expect, solving the equations is going to be a little bit trickier. But we'll see. So step one was to make sure we know the functions that we're dealing with. So the objective is f of xy is, just going to copy it, all this. Oops, let me try again. Doesn't fit. Okay, of course it doesn't. Man. Okay. Should have just written it. There's your objective. Now your whatever it's called, constraint. We want to write our constraint the proper way, right? So we have 20x plus 4y equals 216. You want it 20x plus 4y minus 216 equals 0. Although if you don't, nothing happens on this one because it's a constant on the right. You need all your variables on one side. Okay, so there's our objective and there's our constraint. So yeah, and that's also g of xy. Okay, then what do? We need to figure out the gradients, right? So we need the gradient of f, and we need the gradient of g. So gradient f. So we're taking the partial with respect to x. So derivative of 48x is 48, comma, no x. The derivative of negative x squared is negative 2x. The derivative of 2xy is negative 2y, and that's it. And then for the y derivative, the derivative of 96y is 96. The derivative of negative 2xy is negative 2x. And then the derivative of negative 9y squared is negative 18y. All right, so there are your partial derivatives. We also need the gradient of g. So gradient of g, so partial with respect to x is 20. Partial with respect to y is 4. So that's nice, right? Wait, hold on a second here. Oh, okay. They divided everything here by 4. So they have a different gradient. Doesn't matter. Okay. So we have the gradients, right? So then the equations that we have to solve are as follows. So our system is, we know gradient f equals lambda gradient g, and g equals 0. Or start filling this stuff in. The gradient f is 48 minus 2x minus 2y. 96 minus 2x minus 18y equals lambda 24. And then the other equation is the constraint. So whatever it was, 20x plus 4y um, minus 216 equals 0. All right, so there you go. But remember that actually this splits up into two equations. So when you actually split it up, you got 48 minus 2x minus 2y. That's the x component, right? You're dealing with the x component here and then the x component here. So equals lambda times 20. Then you got 96 minus 2x minus 18y equals lambda times 4. And then you've got 20x plus 4y minus 216 equals 0. And so there we go. So we could solve this using any kind of method that you want. So this is, same thing as before. Like, how would we do this? So we could, if we number these, like, I don't know what the most straightforward way to solve these is. If you've taken linear algebra, you can solve this pretty quickly, but we haven't, so we're going to do long method. So let's see here. I think the way to do this is because I see the equation 1 and equation 2 both have a 2x. So I think what I'm going to do to solve this, which I guess we're on the next part now, 3, solve equations, is if I subtract 1 and 2, I'm going to eliminate, oh no, I don't, hold on. What if I, okay, what if I do this? What if I do equation 1 minus 5 times equation 2? Okay, so what will that look like? I'll have equation 1, which is 48 minus 2x minus 2y equals 20 lambda. And then I'm going to subtract 5 times 96 minus 2x minus 18y equals 4 lambda. So you can see why I'm multiplying by 5, right? Because I want the lambdas to cancel. So I'm going to get 48, when I add these up, at 48 minus 5 times 96, which is negative 432. And then I've got negative 2x minus 5 times negative 2x. So that's going to be negative 2x plus 10x, which is 8x. Then you're going to have negative 2y minus 5 times negative 18. So that's going to be negative 2 plus 5 times 18. So that's 88. So that's going to be plus 88y equals, and then you've got 20 lambda minus 5 times 4 lambda, which is 0. And that was the point, is that you get 0. Okay, so I'm just going to check here. All these are divisible by 8. All the numbers there. Let's just divide by 8 to make the number smaller. I get negative 54 plus x plus 11y equals 0. And so let's give that equation a number. We have so far only 1, 2, 3, so this must be about 4. Okay, so now equation 3 and equation 4 only have x and y variables. Okay, so we see not only, but 3 and 4 have x and y only. So what we want to do is eliminate one of those variables. So just looking at the 3 and 4, like 20x, I would have to multiply this by 20 to get a 20x. I don't really want to. This has an 11y. This has a 4y. Those don't even go, like they're not like terms or anything. So I guess we will. So what if we take equation 3 and then we subtract 20 times equation 4? I mean, it'll work, right? That'll work. So let's do equation 3 minus 20 times equation 4. So equation 3 is 20x plus 4y minus 216 equals 0. And we want 20 times equation 4, which is the one we just came up with. I'm going to multiply everything by 20 right now, just to save myself some work. So if you do, no, I won't, lied, minus 20 times. And let's at least put them in order though. So like the x can come first, and then the y can come second, and then the minus 54 can come third. Okay, so we're going to do this, and we're going to eliminate the x variable. So the point of doing this is that 20x minus 20 times x is going to be 0 right there. But then you've got 4y minus 20 times 11. 4 minus 20 times 11. 4 minus 20 times 11 is negative 216. Y. And then you've got negative 216 minus 20 times negative 54. So negative 216 minus 20 times negative 54. 864 positive. So we get this. Now, this equation only has y in it, which means we can just solve it now. So solve for y. And we will be half done, really. So solve for y. So you got 864 equals 216y. So y is 864 over 216, which 864 over 216, 4. So you get 4. Now, once you have the 4, for y, we need to get the x. You can get the x from equation 4 or equation 3, whichever one you want. So I'll just plug this into to get x. Okay, so where's equation 4? Here it is. It's just the one that has x and y. That's why we're using it. So you plug that in. You have negative 54 plus x plus 11 times 4 equals 0. So you have negative 54 plus x plus 44 equals 0. So you have x minus 54 plus 44 is going to be negative 10. So x minus 10 equals 0. So x equals 10. So you have that. So when you do this, what you're going to get is you have the x and you have the y. Now, one thing to notice is, what's lambda? Where did I find lambda? Right? 3 equations, right? 3 equations, 3 unknowns. X, y, lambda. I found x. I found y. What's lambda? We didn't find it, right? We just didn't find it. So the thing about lambda is the Lagrange multiplier. You don't need it for anything. If you find it along the way, fine, but you don't need it. It's not your answer, right? Lambda was a made-up variable that we made up just to solve the problem. So if you happen to find it, good. If you don't, who cares? It's not for anything. Okay, so we didn't find lambda yet, but who cares, right? Lambda was just a tool to help us solve the problem. Okay, so continuing on then, what we've got is our solution is x equals 10, y equals, it was 4, right? For the xy, that's going to be the x and the y that maximize profit, right? So 10 comma 4 is the xy that maximizes profit. And then the other part of the question is what is the maximum profit is, and it's f of, well, you put in the 10 and you put in the 4. But you actually have to go, you just have to work that out. So you have to go to your original, what is f, way up here, duplicate that. So that's your f, and we just need to work it out. So it's going to be like 48 times 10 plus 96 times 4 minus 10 squared minus 2 times 10 times 4 minus 9 times 4 squared. And if you work this all out, I'm not going to work it out. It works out to 540. Okay. And we didn't write down, like I didn't write down the entire word problem part, but the profit was given in, where is it? Thousands of dollars. So that's the max profit is 540, and that's thousands of dollars, which I didn't write until now, but I am writing it now. All right, so that is your answer to the question. And that's Lagrange multipliers. So lots of fun. What I'm doing right now, real quick, is I'm logging into Newton, and I'm going to check the homework that I assigned to you to see if I assigned you the ones with 2 constraints or not. We'll see. How do I do that? Manage Lagrange multipliers, which is somewhere. There it is. Yeah, it's in there. Okay, so what if you have 2 constraints? So if you have 2 constraints, then it's the exact same thing, but there's an extra equation. So let's write it. Let me scroll to where it is. Yeah, okay. So Lagrange multipliers with 2 constraints. Okay, so what we're trying to do is it's the same setup. So we're trying to maximize this. So let's say find max or min of, let's just say f of x, y, z. They're using 3 variables here. I don't think it matters. Oh, okay. Yeah. So, yeah. So maximize or minimize, you know, of f of x, y, z, subject to um, two constraints: g of x, y, z equals 0, and h of x, y, z also equals 0. Right. So that's like the type of problem that you're solving, and it's the same. It's the same idea, except that the Lagrange multipliers equations are more complicated. So what you have to do is, so this is like before, but your system of equations is as follows. So your system of equations is, where is it? So you need the gradient of f of x, y, z, I guess x0, y0, z0, is equal to lambda 1. There's two lambdas now. Gradient g, x0, y0, z0, plus lambda 2, gradient h, x0, y0, z0. And then you also have both constraints. So you have g of x0, y0, z0 equals 0, and also h of x0, y0, z0 equals 0. So obviously you've got an extra variable, and that means there's an extra equation, and then there's also two separate constraints. So this is, 5 equations and 5 variables. So it's, could be quite a bit harder to solve. Right? So you have x, y, z, and then your other two variables are the lambda 1 and the lambda 2. And even though you don't care about them, right? Just like the previous problem, you don't care about lambda 1 and lambda 2, you still have, you still might have to find them. So let's try one, see how it goes. Example. Find the max and minimum of f of x, y, z, so function of 3 variables now, equals x squared plus y squared plus z squared, subject to your constraints, which are z squared equals x squared plus y squared, and your other constraint is x plus y minus z plus 1 equals 0. So it's a constraint. Okay, so we're going to try to solve this, and just with the same method as before, it's just a little bit more complicated. Okay, so we have our function here, right? F of x, y, z, x squared plus y squared plus z squared. Your constraint, your first constraint is right here, but it's not written in the correct form, right? Like it should be g of x, y, z equals 0. So you actually have to either move the x and the y over to the left or the z over to the right. I'll move the z over to the right. So we'll go x squared plus y squared minus z squared, right? And that's going to be equal 0. But yeah, okay. And then you got h of x, y, z, which they actually did write in the correct form, x plus y minus z plus 1 equals 0. Okay, so those are your two constraints and your objective function. So objective, constraints. All right, so new thing is having two constraints and also having an xyz. So once we have that, we want to write our system of equations, right? Which means we need gradients of everything. So we need the gradient of everything. So gradient f. Oh, that's easy. So f is right here. So partial with respect to x, 2x. Partial with respect to y, 2y. Partial with respect to z, 2z. All right, so easy gradient. Then we need the gradient of g. Well, very similar, right? X squared, y squared, and then it's negative z squared. So when we find the gradient, it's going to be 2x, 2y, negative 2z, like that. And then you got your gradient of h. So partial with respect to x is 1. Partial with respect to y is 1. Partial with respect to z is minus 1. All right, so you find your partials. After you find your partials, what you want to do is you want to write out your system of equations. Right? So your system is, we know, gradient f equals lambda 1 gradient g plus lambda 2 gradient h. And then also you have g equals 0, h equals 0. So that's what it is in general. So for us, what is it? So the gradient of f is 2x, comma 2y, comma 2z equals lambda 1. And then gradient g, which is 2x, 2y, negative 2z plus lambda 2, and then your other gradient, which is 1, 1, minus 1. And then your other constraints are x squared plus y squared minus z squared equals 0. That's g. And then x plus y minus z equals 0. Okay, but remember that first equation is actually 3 equations. Or if you separate it out, like you've got your 2x, lambda 2x, lambda 1, right? Like that's your first equation. So 2x equals lambda 1, 2x, plus lambda 2 times 1, which is just lambda 2. Second equation is going to be the y's. So 2y, 2y, lambda 2y, the 1. So we got 2y equals lambda 1, 2y, plus lambda 2. Third equation, 2z equals lambda 1, negative 2z, minus lambda 2. So we've got a couple sign changes there. And then you got your x squared plus y squared minus z squared equals 0. And then x plus y minus z equals 0. So how are we going to do this? So, I mean, there's different ways, right? We could do lambdas. So, hold on here. Let me see what they do to see if what they're going to do is smarter than what I'm going to do. No, they just, okay. I mean, I don't see. Um, oh, because there's two lambdas. The first three equations contain the variable lambda 2. Um, yeah. Okay. Yeah. So let's think about this. Okay. Yeah. So there's a lot of ways to go about this. It's going to be there's not like any magic shortcut. So like if I just number them 1, 2, 3, for 5. What you can do is you can solve one of these first 3. Well, I think we're going to take number 3, solve it for lambda 2. And after you solve it for lambda 2, you can substitute that into the equations 1 and 2 for lambda 2. And then you're going to have no more lambda 2's anywhere. So we can get rid of the lambda 2 basically. So that's our first step. We're trying to get it down from 5 variables to 4, from 4 to 3, from 3 to 2, from 2 to 1, and then we'll have hopefully something we can solve. So that's the game plan. All right, so solve, right? Okay, so we're going to solve 3 for lambda 2, and then I'm going to substitute that in equations 1 and 2, and then we'll get rid of lambda 2 that way. Okay, so that's our first mission. So solve 3 for lambda 2. So the way you would do that is you'd move lambda 2 over. Actually, let me just copy this. All right, so solve for lambda 2. So you put the lambda 2 on the right, left, and then on the right, you're going to have negative 2 lambda 1 z from right here, and then I'm going to move the 2z over. So I did it. Now I'm going to take that result there, which I better call, I guess, 4. No, wait, we're already up to 5. So 6, equation 6. Substitute that into equation 1 and 2. So sub that into 1. So equation 1 is up here. So here's 1. And we're going to substitute that in for the lambda 2. Oops. So we're going to substitute that in for the lambda 2. Hey, back up. Okay. Right there. Right there. Substitute it in. So we do that. We get 2x equals lambda 1 times 2x plus lambda 2. But lambda 2 is minus 2 lambda 1 z minus 2z. Although I feel like, okay, let me look at this one more time. Is this really the best way? Yeah, I think it is. Okay. Okay, so this is what we get. What can we do with it? Not a lot. Everything has a 2. Divide everything by 2, we get x equals lambda 1x minus lambda 1z minus z, I think. So that's equation 7. And the point is that equation 7 has no lambda 2 anymore, just lambda 1. Okay, now we're going to sub 6 into equation 2 as well. So let's get equation 2. So here's equation 2. So we got 2y equals 2 lambda 1y plus lambda 2. But lambda 2 is equation 6. So it is negative 2 lambda 1z minus 2z. Again, everything has a 2. Divide everything by 2. So y equals lambda 1y minus lambda 1z minus 2z. And let's give that a name. Call that 7. Nope, 8. Okay. So we got those equations 7 and 8. So the thing about equations 7 and 8 is that they don't have any lambda 2, right? So they've got only lambda 1 and xyz. Okay. what are we going to do with that? So that's got lambda 1 and xyz, lambda 1 and xyz. Is there something else with lambda 1 and xyz? No. So what can we do with that? I think what we have to do is we have to substitute that in for x and y in equation 4 and equation 5. So what we just got for 7 and 8, we need to substitute in for x and y in equations 4 and 5. Think that'll work, because that what that'll do is it will wait, will that do anything? What will that do? Um, okay, so we have x lambda 1 z and y lambda 1 z. Oh, okay. We need to get rid of the lambda 1 somehow. Oh, that's not going to be possible. Oh, okay. I see what to do. Okay, I see what to do. Yeah, the algebra on these can be tough. But here's what we're going to do. So on 7 and 8, we can solve for lambda 1. So on 7 and 8, the ones we were just working with, we can solve for lambda 1. Because they both have a lambda 1. So let's start with the 7. So equation 7 is x equals lambda 1 x minus lambda 1 z minus z. So if you're trying to solve this for lambda 1, you would move the z over to the left. So you'd have x plus z equals lambda 1 x minus lambda 1 z. Then you could factor out a lambda 1, and you get this. And then you can divide by x minus z, and you get lambda 1 equals x plus z over x minus z. Okay, and that's going to be, we're up to 9, equation 9. Do that same exact thing for equation 8. So equation 8 is, I think, y equals lambda 1 y minus lambda 1 z minus z. Let me check. Lambda 1 y minus lambda 1 z minus 2z. Wait, is it supposed to be 2z? What happened? Oh, no, there's a typo right here on equation 8. Okay, so that's correct. So we're going to solve for lambda 1 here. So same thing as before. We're simply going to add z, so you get y plus z equals, and the remaining terms here have a lambda 1, factor out the lambda 1. So you get this, and then divide by y minus z, you get lambda 1 equals y plus z over y minus z. Now, why do you care about that? I think the reason you care about that is because now you've got two equations. You've got two equations in equation 9 that are solved for lambda 1. So if they're both equal to lambda 1, that means you can set them equal to each other, right? So that's what we're going to do. We say we see 9 and 10 are both equal lambda 1. So set them equal to each other. Right? So what you're going to end up with is, from equation 9, you're going to end up with x plus z over x minus z equals lambda 1, right? Which is equal to y plus z over y minus z from equation 10, right? So this equals lambda 1, but lambda 1 equals this. So they're equal to each other. And then you can just kind of throw out that lambda 1. So you have x plus z, x minus z, y plus z, y minus z. Great. But what you can do here is you can get rid of the fractions as well, just by, you can just take this, move it up, and you could take this and move it up, and you'll get y minus z, x plus z equals y plus z, x minus z. Or if you multiply that out, which I guess we have to, you're going to end up with, you have to FOIL it. So xy minus xz plus yz minus z squared equals, and then on the other side, xy plus xz minus yz minus z squared. And when you simplify this, there's a lot of stuff's going to cancel because it's on both sides. So like the z squared, negative z squared, is going to cancel with negative z squared. You've got an xy cancels with the xy. So you've got, what do we have? On the left-hand side, yz minus xz equals xz minus yz, like that. So you can factor a z out of both of these. Or if we put everything on one side of the equation, actually. So put everything on one side of the equation, you're going to get 2yz, right? When you move this over, and you're going to get minus 2xz equals 0. And from there, you can factor out a 2z and get y minus x equals 0. Now, that was a lot of work, but we actually got somewhere because this actually tells you two things. This says, so this is a good result. This says either z equals 0 or y minus x equals 0. And what you got to do is you actually have to consider both possibilities. Okay, so we got to start with 1 and then pursue it till the end. So let's consider z equals 0. Start with z equals 0. So if z equals 0, let's scroll up and look through our other equations and see if we can figure anything out. So we have z equals 0. Could we put that into an equation somewhere? Well, what would equation, if we got an equation here, like equation 8, if z equals 0, that would be 0, that would be 0, and you have y equals lambda 1y, which would either tell you y equals 0 or lambda 1 equals 0. Don't know if I like that equation though. Let me scroll up, see if we can come up with a better idea. Well, if z equals 0 here, that would get us something. Okay, yeah, what we want is this one. This is the one we want. So we're gonna take z equals 0 and go all the way up and plug it into equation 4. So plug into, now why do we want 4? Well, equation 4 was x squared plus y squared. Was it minus z squared? I think so. Minus z squared equals 0. Well, we're too far, right? Where is it? Yeah, equation 4 is minus z squared. Okay, so if you put z equals 0 in there, you've got x squared plus y squared equals 0. Now, the thing about x squared plus y squared equals 0 is it only has one solution. The solution is x equals 0, y equals 0. So the only solution is x equals 0, y equals 0. So if you combine this information here, if z equals 0, then x and y also have to be 0. So what we find is one possible point here. So x, y, z equals 0, 0, 0 is possible solution, right? Possible maximum or minimum. So that's a possible maximum or minimum. So this is important. We're going to hold on to this point for later. And that's what happens if z equals 0. So notice what I did there was I just scrolled up through all the equations looking for what I wanted to plug in z equals 0 into, looking for what would give me the best result, right? So like when you're looking at all of the equations you have, like you have z equals 0. So like plugging z equals 0 here just gives you x plus y equals 0. Well, that says x equals negative y. All right, that's fine. But that doesn't tell you an answer immediately. If you plug z equals 0 here, you just get 0 equals 0 minus lambda 2. So you find out that lambda 2 is 0. Okay, lambda 2 is 0, but what else is that going to get me? I don't really care about lambda 2 anyway. So like it's not immediately obvious what that's going to get me. So I don't like plugging z equals 0 in here. There's no z's to plug in. There's no z's to plug in. Plugging in z equals 0 here just gives you that lambda 2 equals 0, which is fine, but not an answer. This third one gives you that x equals negative y, which is something, but again, not directly an answer. And this one right here, when z equals 0, gives you x squared plus y squared equals 0, which you should know only has one solution, 0, 0. So that's why we ended up with that one. So I just considered all of my possible equations and picked the one that looked the nicest. But if you pick the wrong one, you just, keep going until you'll eventually get to the answer anyway. All right, so that's what we got from z equals 0. Our other possibility, though, was that y minus x equals 0. So in that case, other case, x minus y equals 0, or x equals y, right? That's the same thing. So you have x equals y. And just like before, I'm going to scroll up and try to find a place to plug that in where I think I'll be able to figure out what x, y, and z are. So we're looking for where we can do something good by replacing x's with y's. Like, for example, equation 8, if you replace the y with an x, you get x equals lambda 1x minus lambda 1z minus z. So what? Because that's actually what you just get the same equation as equation 7. So replacing x equals y in 7 or 8 doesn't give you anything new. So you don't care about 7 and 8. Equation 6 doesn't have any x's and y's, so we are not going to use that one. This does. But if I replace x with y here, I'm going to get like 2y minus z equals 0. That's something. If I replace x equals y here, I'm going to get something. I don't see anything good coming up here by replacing x with y. So I don't immediately see anything great out of the first three. I think we're going to have to go with the 4 and the 5. So let me just copy these. I think that's where the best results can be obtained by plugging in x equals y. So let me just write those down. We'll move them out of the way. I lost part of it. Okay. Oh, also this. Okay, so x minus y. All right, so let's plug into 4 and 5. So let's plug x equals y into 4. So I'm going to replace the x with a y. So I get y squared plus y squared minus z squared equals 0. Or I get 2y squared minus z squared equals 0. Or moving the z squared over, I get 2y squared equals z squared. And we can leave it like that. Or if you want to square root both sides, you can, but you'll get a plus or minus, right? You'll get like z equals plus or minus square root 2y squared. So z is plus or minus square root 2y. So that's what you get for equation 4. Let's also plug x equals y into equation 5, and maybe something good will happen. So equation 5 is down here. So we're replacing x with y. We get y plus y minus z equals 0. So you get 2y minus z equals 0. So you get, moving the z over, you get z equals 2y. Now, when I get z equals 2y, that makes me want to come back here. I don't even need these, so maybe I'll just kind of, we did that, but who cares? So I've got these equations here. If I call this, I don't even know what equation we're up to, 10, 11, 10. So like if I call this 11 and this 12, we can substitute 12 into 11, for z, for z, for circle z. Okay, so you've got this equation, right? You've got equation 11, right? Which is 2y squared equals z squared. But if we replace the z with 2y, then you end up with 2y squared equals 4y squared. So you see we're getting somewhere here. Something terrible has happened to me. I think I lost a number somewhere in one of the equations. Hold up, I think I did a mistake. Oh man. Okay, bummer. Okay, I made a mistake at the beginning of the problem. H is x plus y minus z plus 1 equals 0. And when I wrote down the system of equations, I wrote x plus y minus z. I left off the plus 1. And that didn't matter anywhere until where we are now. I have to move this over, fix it with the plus 1 there. Fix it with the plus 1 there. And then now we can continue on, but I have to go fix what we just did here. This last little bit. So I've got to just erase all this. So 5 is actually this. That 1 was not there. Okay, so when we substitute in 5, we got this 1. So I actually have 2y minus z plus 1 equals 0. Or if you solve this for z, you get z equals 2y minus 1. Right? So now that you can substitute into 11. So we're not, we didn't lose a lot of work. So substitute that in for z in 11. So 11 says, so for 11, you've got 2y squared equals z squared. But z is 2y minus 1. Okay, and then now this only has y. We should be able to solve for y now. So you get 2y squared equals 4y squared minus 4y plus 1. Move the 2y squared over, you get 0 equals 2y squared minus 4y plus 1. Okay, now you have to solve this with the quadratic equation, and in the interest of time, I'm not going to. I'm just going to tell you the answer. So just solve with quadratic equation. Okay. When you solve that with the quadratic equation, you're going to get y equals something. You're going to end up with, after it's all simplified, you end up with -1 plus or minus square root 2 over 2 for y, right? So that's just the quadratic equation. Now, once you have that, remember that we were in the section here, x equals y. And don't forget x equals y. So you also have x equals -1 plus or minus square root 2. The same one as y, whatever y equals. Okay. And then also you need the z. What was z? Actually, let me just do this. Actually, let me erase what we just did. All right. So we got our solutions. So one of them is this. So solutions. One of them is y equals -1 plus square root 2 over 2. Now, if that's the y value, the x value is also -1 plus square root 2 over 2 because x equals y. And then the z, how would you get the z? We have an equation relating z and x. It is z and y, actually, it's right here. Z is 2y minus 1. So z is 2y minus 1, which is 2 -1 plus square root 2 over 2 minus 1, which is -2 plus square root 2 minus 1, which is -3 plus square root 2, I believe. Did I do that wrong? Yes, I did that wrong. This is supposed to be a 1. Plus 1. Wait. But if that's true, this is plus. And if that's plus, this is plus. And this is plus. I'm glad I didn't do it myself. This is still the right answer. Man, it's so easy to make mistakes on these. So this would be a plus. So that's a plus 1. So that's a plus 1. So this is a minus 1. Okay, so what do we get here? We actually get x value -1 plus root 2 over 2. Y value the same, -1 plus root 2 over 2. And then -1 plus root 2. Now the other solution, so it's two of them. And the other one was with the minus, right? Because this is a plus or minus here. -1 minus root 2 over 2. The y value is the same. And then if you do that, I'm just going to tell you the answer. It would be -1 minus root 2. Okay, terrible. Okay, so what do we got? So the punchline here is that we now have all of our possible solutions. So all the minimums and maximums of f of x, y, z occur at these two, and also 0, 0, 0, right? Don't forget we have 0, 0, 0 as well, right? So these 3 points. And how would you figure out which one is which? So you would take all of these values and you would plug them in into the original function f. And so you get like f of 0, 0, 0. I'm just going to tell you the answer. F of 0, 0, 0. Where's f? Oh, f was x squared plus y squared plus z squared. Right, so this is, the original function was simply x squared, y squared, x squared plus y squared plus z squared. Okay, so f of this one is, again, there's a lot of work, right? You actually have to plug that in and work it out. So it's very tedious. But this one, the one with the pluses, happens to work out to 6 minus 4 root 2. And then if you do the other one, okay, good enough. If you do the other one with the minuses, that one works out to 6 plus 4 square root 2. Okay, and so if you compare these like as decimals here, so like if you do 6 plus 4 times square root 2, this is about 11.65. And if you do 6 minus 4 square root 2, that is about 0.343. Wait, why did they throw out 0, 0, 0? Hold on a second. Oh, okay. Yeah, also, it turns out that because 0, 0, 0 didn't work, because equation 5, once I fixed equation 5, because of that missing plus 1, you like 0, 0, 0 doesn't satisfy this, right? Because 0, 0, 0 would leave you with 1 equals 0, which is incorrect. So I have to go back down to the 0, 0, 0 here. We found 0, 0, 0, and I said it's a possible maximum or minimum. And then no, because 0, 0, 0 does not satisfy equation 5. Okay, so when you come down here, this is not on the list. So this is not on the list. So you only have actually these two numbers. So you plug these two in, the ones that actually work, and you get around 0.3 and you get around 11.65. So one of them is the maximum and the other one's your minimum. So max, minimum. Okay, so that is that. So I think that's enough Lagrange multipliers for today. I didn't think about doing these ones with two constraints, but you can see that two constraints is going to make it, quite a bit more work. And the way you can save time and energy is by solving some of these equations on a computer. I'll try to post another video where I solve these on a computer a little bit to help you out. But most of them should be pretty straightforward. And yeah, so I'll see you in the next video.